Okay. Good evening. It's another Advent of Code. We've got a minute and 13 seconds for day 8. Day 7 yesterday, you may notice that I now have both stars. I realized, as I was falling asleep, that the problem was a lot more simple than I thought it was. Leading to this commit. I so don't want to do this right now. Cool. Leading to this commit. Yeah, so it was a lot simpler than I thought. All I had to do actually was just concatenate, do the concatenation logic just on the next number instead of doing any of this weird fancy stuff that I was trying to do that didn't end up working. Anyway, so that's how day 7 went. Ended up being a lot simpler than I thought for part 2. We're now on to day 8. As always, Advent of Code is a daily advent calendar through the month of December. The problems get progressively harder. Today's day 8, and we'll see how hard it is in 2 seconds. 1, let's go. We're on the roof. All right, it's another graph problem. Scanning across the city, we find there are actually many such antennas. Each antenna has tuned to a specific frequency. Assume a lowercase letter, uppercase letter, or digit. Get a map of these antennas. Cool. Only applies to the various effective specific antinodes based on present frequencies of the antennas. The antinode occurs at any point that's perfectly in line with 2 antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are 2 antinodes, one on either side of them. Any pair of antennas with the same frequency, there are 2 antinodes, one on either side of them. Create the 2 antinodes. Okay. Perfectly in line with 2 antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This part doesn't quite make sense to me yet. For the reason that I don't understand how they could be... like, they're not perfectly in line. Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map, so instead it only adds 2. At any point, it is perfectly in line with 2 antennas of the same frequency. But only when one of the antennas is twice as far away as the other. So how is this perfectly in line with either of these? That doesn't make sense to me. Only one of the antennas is twice as far away as the other. So this is, what, 2 away, and this is 4 away. But it's not in line. That's the part that doesn't make sense. Antennas of different frequencies don't create antinodes, and okay, sure, antinodes can occur at locations that contain antennas. Sure. So that's the topmost A frequency antenna overlaps with the 0 frequency. Oh, because the topmost A frequency. There are 14 total unique locations that contain an antinode within the bounds of the map. How many unique locations within the bounds of the map contain an antinode? Okay, so I don't understand this. Each antenna is tuned to a specific frequency. Based on the measurement. At any point is perfectly in line with 2 antennas of the same frequency. Only one of the antennas is twice as far away from the other. In line with 2 antennas of the same frequency. Any pair of antennas of the same frequency, there are 2 antennas, one on either side of them. These aren't perfectly in line. I mean, I guess they sort of are, but it's like... it's like a weird... it's a weird line. How the heck am I gonna do this problem? It's like this weird slopey, you know, it's 2 across, sorry, 3 across and 1 down. Does that hold for all of them? 3 across and 1 down. Okay, all right, sure. So we just need to make... Okay, that actually sort of makes sense. So to get to this point, we just have to get the distance between this and then add it to this for the closest one, if that makes sense. So, oh, sure, okay. So what just made it click for me is that if I look at this, any other... So from this node, I go 3 up and 1 across, and I hit this. From this node, if I go 3 down and 1 across the other direction, I hit this. And so this is where the antinode is. That's how I'm going to reason about it. Okay, I think that's doable. I wouldn't say it's perfectly in line with 2 antennas at the same frequency. That's kind of a weird way of phrasing it, which threw me off. But I think that makes sense now. Whoa, that's so not what I wanted. Hello? Come back. Alright, well. Here goes my entire desktop. Okay, so... cool. So let's... We need... Oh my goodness. Okay, so let's reason about it like this. Get sets of coordinates that an antenna occurs at, or that each flavor of antenna occurs at. And how big is our input? Because that might inform our approach. Okay, so that's actually not too huge. Once we have the sets of coordinates, we want to, for each pair of coordinates, we need to get the antinodes for each pair. Add them to a set of 14 total unique locations. So it doesn't count if 2 antinodes are in the same place. Antinode overlapping autonomous. Okay. So they can overlap antennas, but we only count, like if there's 2 antinodes in the same place, we only count them as 1. Antinodes. So this only counts if it's on the map. And then count size of that set. Okay, so let's see. So we need antennas, or we'll call those flavors to be interesting. So this will be a list of, so this will be like A, and this will map to a list of coordinates like 1, 2, 3, 4. So this will just be all the coordinates that have the antennas that match this color, or flavor rather. For row and lines, for call in row, we're gonna do range length of lines. And the same here. So this is going to be line 0. I mean, row would also work, doesn't really matter. We are going to, if, we'll do char is lines, row, column. If char not in flavors, we will do flavors. Char becomes an empty list, and then we'll add the coordinate for each type of antenna. And then we will add dot append, and this will be row column. And then let's just print flavors at the end here to make sure that this is working. I expect it will because it's pretty straightforward. We haven't really done much yet. Cool. Oh, because I didn't put anything in my input. Yeah, that makes sense. We also need to, so if it's not a dot is what we need to check for. If jar is just a dot, we can continue. And I still didn't put anything in my input, so sure, that makes sense. This should just be a dot because we haven't actually. Cool. That looks right. 3, 4, and 5, 5. Yeah, we'll take it. Okay, so next thing we need to do is get the antinodes for each pair. This is a little bit weird to reason about. So one thing we want to do is get the Manhattan distance. Manhattan distance is the distance in x and y coordinates between these two. So it's this distance and this distance. So added together, that makes sense. So like Manhattan distance between this A and this A would be 1, 2, 3, because it's 2 down and 1 across. But we don't actually want Manhattan distance. We want like XY distance. So we'll call this XY distance. So this will return like returns XY diff between points. So this will give us the X and Y coordinates that differ between P1 and P2. So that'll help us calculate the antinodes. I think this is really easy. I think we just want to return P1 0 minus P2 0, and then the same thing but for their Y coordinates. So that should be fairly straightforward. And then what we want to do with that is, and then for each, there's like a Python helper function. So we need to, once we have our flavors, for key in flavors, we want to do for, just have to check every pair of coordinates, set antinodes, called a day. Flavor, I guess. So for all the A's, we need to check it against all the other A's and then get the antinodes. So we need to, I think there's a, there's like a collections.permutations or something. Python collections, what is it? Combinations. There's just an easy way to get the number of, or each combination. Yeah, this is what I'm looking for. Permutations ABCD2. So this will give us all of the ways that we can make 2 letter strings from ABCD. With replacement, so this is saying CB is the same as BC, so this is what we want. So we don't care if they're the same coordinate, we only want each set to be considered once regardless of order. Cool, so we can import iter tools. This is just a built-in Python module. It's good to know about these things, because sometimes, I mean, especially if you're going to be doing problems like this, because they're often helpful. Let's do pairs is iter tools dot accommodations to the replacement of flavors. Let's see what this does, and then let's print pairs. So this should give us, okay, well, it's going to give us 3 and 4. And char, or I'm just patching this a little bit so that I can put in the antinode example that they give without having to do any extra work. Oh, right, I need to tell it 2. Combinations, replacement, flavors 2. So this should give us like this pair, and that should be it. Oh, because I've got to convert it to a list. Sure. Oh, right. So it should be flavors key. Aha, so it doesn't quite do that. Wait, am I doing this wrong? I don't think it should be with replacement. I think replacement is not what we want. I think combinations. This should just be combinations. Because, yeah, replacement's not what we want, because that can include the same thing twice. Okay, 3 4 4 8 3 4 4 5 or 5 5 rather 4 8 5 5. That seems right to me. Yes, so that should be the locations of all of our nodes, our antinodes, or rather, that's not the location of the antinodes. That's the offset from each pair. That makes sense. So really, we should see there should be 3 more, except they would be off the. Okay, yeah, 2 are off the right side of the map, so instead it has only 2. Yeah, cool. Right, that's... Wait, hold on. Wait a sec. Why do we... Oh, because... Alright, sure. Alright, so I want to see if I can get to here from these numbers. What I think we can do is just add... So, sorry, this gives us the pairs, and then from these pairs, we need to get the XY distance, and then we need to add that positive and negative to the coordinates of each pair, and then see if that's on the grid. If it is, we'll mark it, and if it's not, we won't mark it. Hopefully that made sense. Okay, for P in pairs, we will do distance is XY distance of P0, P1, and then we'll do antinode 1. So we're going to have 2 antinodes. We're going to have antinode 1 is P... Okay, so let me think about this. So we're getting the distance between P0 and P1. The first antinode is going to be the first point minus the XY distance, because we want to go in the other direction between the 2. So this is going to be P0, 0 minus distance 0, comma P1, 0. This is a little bit rough distance-wise. Sorry, P0, 1. A little bit rough syntax-wise. But I think it's okay. And then the other one's going to be P1 and plus. And let's print these and see... what happens? Antinodes, and this will be, we'll just call this A1 and A2 because that's shorter. Then we don't need the pairs. Okay, let's see if that makes sense at all. Maybe. Well, okay, so immediately we're not right because we don't have any 3, 0. But I'm curious to see where we ended up. 4, 8. Okay, well, let's do for pair. And then pair is P. So this is for 3, 4. 0, 1, 2, 3. Sorry, this is rows and then columns. So 0, 1, 2, 3, 4. Okay. 3, 4, and 4, 8. So that's this one. So we're saying that the antinode is... That is so not it. So maybe our distance is wrong. So this is our distance. Oh, right, because it's times 2. Yep. So this should be... Should we just multiply that by 2? I think we'll multiply that by 2 and call it a day. Right, because if we just take the distance from one to another and we use that for our offset, we're going to end up at the same place. No, that doesn't seem to do it either. 5, 12, 0, so that'd be 6. That'll be off, and 2, 0. Actually, 0, 1, 2, 0. Okay, so that seems to actually do it. Cool. Yeah, all right, so let's plot these on our grid and see if that's the right thing that we end up with. Like, we'll print it out and see if that's right, and then if it is, then we'll be fine. Okay, acapella, get the heck out of here, buddy. Cool. Okay, so the last thing we need to do is make sure that the antinode is on the grid. For node in A1, A2. And then we'll check if the 0 is less than or equal to A1. 0 is less than or equal, no, and is less than rows is this way, so it's going to be length of grid. This is going to be lines. And the same thing for the columns. 0 is less than or equal to node 1, length of line 0. So if this is all true, then we can put it in antinodes is this. We can go antinodes. Let's do this as a string key because that seems better to me than doing it a different way. So this will be node 0, comma, node 1. Just copy this. And this will just become... Yeah, let's set it to just key. So this is the same of... Oh, we should call this flavor. Because key is kind of an overloaded term here. So, then at the end, we can do... let's print the length of... How are we doing? 922? That's not too bad. Print length of antinodes. I don't know if that'll actually tell us what we want. 4? Yeah, okay, that seems to work. Cool. Let's try with this big input. If we hit 14, I'll be happy. Excellent. So that seems to work. Let's copy this. Try it for the big boy. We can get rid of some of these print statements. 300. Oh, sure. Yeah, okay. 301. Let's see if that's right. Excellent. Part 1's done. Cool. Let's see about part 2. 23 minutes, not terrible. Watching over your shoulder as we work, we took the effects of resonant harmonics into our calculations. After updating our model, translated the antinode at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of distance. Position exactly in line with at least 2 antennas of the same frequency, regardless of distance. This means that some of the new antennas will occur at the position of each antenna, unless that antenna has only one of its frequency. Any grid position exactly in line with at least 2 antennas of the same frequency, regardless of distance. Oh, so they just keep extending. So cool. Okay, so this is the same thing, except we want to do this until we're off the grid, basically. So, hold on, let me copy this all to part 2. Cool, so we need to go up, go down. This doesn't really mean anything except we just need to do it twice. We need to go in each direction. So instead of doing just this, we want to do while we'll call this node, and then we want to do this. And then we'll just keep adding this. Node becomes, or rather we'll have to do this. And then node becomes itself again. Node 0 minus distance, node 1. Except it's not times 2. I think we only want it to, because we've already applied an offset here. Whoops. So I think we only want it to go one more distance away. So, and then this is the same thing. We just want it the other direction as well. Except this now is, whoops, did I? Yeesh. This is plus instead of minus, and I think that's the only difference. And then we've already added the nodes. So we should just be able to print the length of the antinodes. So ideally this should give us 34 immediately. Ideally. Like I said, I didn't say it yet, but I don't expect it to work. 29. Ooh, that sucks. That sucks a lot, actually. Okay, so we're going to start with this puzzle. I create many antinodes. 1, 2, 3, 4, 5, 6. The 3 T frequency antennas are all exactly in line with 2 antennas, so they are all also antinodes. So this should give us 9. Excellent. Doesn't do that. So I wonder if we don't want this times 2. I wonder if we remove these times 2s, if it will give us what we want. All right. Because I guess we want to count these. All right. I don't like the descriptions for this day particularly much. Some of the new... Unless the antenna is the only one of its frequency. Yeah, so this is a little confusing. So basically this means that any antenna position, as long as there's at least 2, counts as an antinode. So I'm wasting time. I should put the puzzle in because I think this solution works. Yeah, I just frittered away a minute or two there. Anyway, cool. We did it. 9:28, not bad. Ooh, I'm fast today compared to y'all. You like to see it. All right. So back to what I was saying about. I don't think this is a look. I think Advent of Code is great, and it's super cool that I think it's just one person running this whole thing still. I looked into this a couple years ago, but my understanding is it's just one person running this, and I think it's fantastic that they've done this and made this available as just a fun little puzzle. But that said, I don't think this is a very well written question or problem, whatever. It's not very intuitive. Or like the examples, I really had to think about what was going on here. Like this section, an antinode occurs at any grid position exactly in line with at least two antennas of the same frequency, regardless of distance. You should just say that, and then this part here where it's saying that each antenna is so basically what I'm trying to say is the instructions should just say each antenna is an antinode unless that antenna is the only one of its frequency. It's talking about this whole complicated part where it has to be exactly in line with two antennas, but all it really means is that if there are two antennas, they're antinodes for the same frequency. And also, you know, any... I don't know how I would phrase it better, but this was confusing, and I think unnecessarily so because of the wording of the challenge. But anyway, still a fun one. I actually like this a lot. This is one of the ones that it seems like, how the heck am I going to solve this at first, the first time you read it? And then you kind of break it apart, and it starts to make a lot of sense. And that's my favorite kind of programming problem to solve. So, yeah, this was a fun one. Not much else to say. We finished early tonight. Would have finished probably around this time yesterday if I'd read the problem right. But anyway, that's day 8. Thanks for watching. Same time.